Next, we will discuss next method. There is a conjugate gradient method, or it is also known as Fletcher race method. Fletcher Fletcher race method. So, so this method, they will come across the term, the name, or the direction, which is we have already discussed. That is conjugate direction, conjugate direction. So, conjugate directions. If you go through these conjugate directions, the function is got minimized, or optimum solution we will obtain the optimum solution in a faster rate. Okay, so that is the characteristics of this conjugate gradient method or Fletcher method, different, which is which is an advantage uh, uh, from when you compare with the steepest descent method or Cauchy's method. Okay, so the we will directly go to the algorithm. So the and we will solve one or two problems in order to understand the algorithm also. Okay, and not going to going into the details of the theory. Okay, that is not required also. The iterative procedure of Fletcher method can be stated as: the first step is, like for any optimization problem, whether it is nonlinear, linear, constrained or unconstrained, we will start with an arbitrary initial point. That is the first step. Start with an arbitrary initial point x1. Now set the first search direction, that is search direction. Second step is to set the first search direction, that is S1. That is equal to the yes. However, we are here also we are making use of the direction of the gradient of a function, right? So here S1 direction will be minus negative of the gradient of f of xi, and that's it is denoted by minus del fi. Okay, now in the third step we will find the point x2 according to the relation, that is the new uh, point, trial point, or the optimum point we will find out according to the relation x2 equal to x1 plus lambda 1 optimum to s, right? Yes, so how you will find out, you refer the previous uh, video. Okay, the previous problem. So it is same for the lambda 1 star, finding this is same. So we will find out this x2 and this lambda 1 star is the optimal step length, the direction s1. Now in the fourth step, set we will set I equals to 2, and we will go to the next step, that is fifth step. We will go in fifth step. Yes, the fifth step, uh, we will find gradient del fi. Del fi we will find out. Actually del fi means here it will be del f2, that is equal to del f of xi, sorry, x is vector capital Xi. Okay, and we will will set set the direction Si, that is S2 equal to minus del Fi plus, right, minus del Fi is the previously chosen direction, that is S1, but Si here S2 will be we will calculate the new direction S2 as minus delta Fi plus del Fi modulus square divided by del Fi minus 1 mod square. That means this in this case it will be del F2 modulus of del F2 square, right, divided by modulus del F1 whole square. Okay, that means its magnitude we will take the magnitude of the gradient function at the x1 solution as well as x1 solution here and x2 solution here on the numerator. Okay, and that into s I minus 1 I minus that means s1, that means we will derive s2 from the previous data we have. From the previous data means we have s1 we have, and also del f1 we have, and also here we have del f2. So from this del f1 and del f2 and also s1, we will derive the new direction s2. Okay, in this given by this formula. This formula. Okay, then the in the next step we will sixth step we will compute the optimum step length again. Step length in this case, that is lambda I star, means here it will be lambda 2 star optimum length. Okay, in the direction Si, in the direction Si, that means S2, in the direction of S2. And we will find the new point and find the new point as xi plus 1, that is x2 plus 1, that is x3 here. Okay, xi plus 1 in general, and equal to xi plus again lambda I star to Si. So in this case what we will get is x2 plus 1 equal to x2 plus lambda 2 star into s2. Okay, this is the this is the value. Then you will get a new trial point or new optimum solution point. Okay, and we will test the optimality for the new point. That means test for the optimality. That means whether the objective function is minimized at this particular point, new point, that is xi plus 1. Test for the optimality of the point xi plus 1. Okay, and if xi plus 1 is if xi plus 1 gives the optimum or if xi plus 1 minimize the objective function, that is it gives the optimum solution, then we will stop the process. Okay, we will stop the process. Otherwise we will go to step step 4. That means we will increase our iteration number from I equal to 2 to I equal to 2 plus 1, that is equal to 3, and we will proceed. We will repeat the uh, the following steps further. Okay, this is the algorithm, and now we will solve one or two problems so that you will get more clarity. The problem is like this: minimize f of x1 x2, two variable function, objective function, that is given by x1 square plus x2 square minus 2x1 x. Okay, and this is the this objective function is not constrained, right? That means there is no restriction, there is no other constraint, and that means it's an unconstrained nonlinear optimization problem, and he has given the starting point as vector 1 0. This is nothing but your x1. Okay, using Fletcher rays or conjugate gradient method. Okay. So given x1 equal to 1 0. Okay, now in order to proceed to the step 1, step 2, step 3, etc., first we have to find out the gradient. Okay, gradient of f, that is del f, that's equal to dou f by dou x1, dou f by dou x2, and that's equal to 2 2x1 x2 2x2 minus 2x, right? So you do the partial differentiation, you will get this. I don't want to do that. Okay, then del f1 that's equal to del f, that is gradient at the point, gradient of the function f at your given initial point x1, and that's uh, equal to, if you substitute for x1 x2 as 1 and 0, you will get it as 2 and minus 2 vector, column vector. Then we will set the direction s1 as equal to negative, we will negotiate the gradient function, that is negative of minus negative of this gradient minus del f1, that's equal to minus 2. Right, now we will find out the new base point, new optimum solution, that is x2 will be equal to x1 plus lambda 1 star s1, that's equal to 1 0 plus lambda 1 minus 2 2, and that's equal to, so we will find out lambda 1 in this case, so that the objective function is got minimized, that is optimum step length we will find out. So that is equal to 1 minus 2 lambda 1 and 2 lambda 1. Okay, and in the next step we will evaluate f of x2. Okay, that's equal to f of x1 plus lambda 1 s1, that's equal to in place of x1 you put 1 minus 2 lambda 1, and in place of x2 you put or you substitute 2 lambda 1. Yeah, then you will, and then you solve or you reduce, then you will get it as 1 minus 8 lambda 1 plus 16 lambda 1 square. So this is again a quadratic function, right? So you can solve it. It will be a function like this. So you can find out the minimum uh, point. Okay, the minimum point. So for the optimum solution, you can find out by Newton's method by differentiating once and again differentiating twice and putting less than zero. Sorry, not yeah. Actually, this is greater than zero. Greater than d square f by d lambda 1 greater than 0 and df by d lambda 1 equal to 0. Right. Yes. So you apply that condition, then you will get lambda 1 is lambda 1 equal to 1 by 4 equal to 0.25 you will get. Okay. Now what now what is the next step? Then you calculate x2 equal to, you substitute lambda 1 in x2 equation here, 1 minus 2 lambda 1 2 lambda 1, then what you will get, 1 minus 2 lambda 1 is 1 minus 2 into 2 into 0.25, that means zero point 0.5 you will get, and 2 lambda 1 means 2 into 1 by 4, that means 1 by 2 again, it is again 0.5. Okay, so this is x2. now now in the next step what we will do is 0.5 0.5 we will we have the new base point. So we will find out, we will evaluate such that we will examine that whether we can stop here, or you have, or either you have to proceed for new base points like x3 x4 x5, or you can, whether you can stop here. So in order to uh, find that, we will find out the new direction, that is s2, or in order to find out the new direction s2 you have to find out the gradient of the objective function at x2, at the point x2, and it is denoted by del f2, and that's equal to del f of x2, and that's equal to, okay, that means gradient of f at x2, that means gradient of a constant, gradient del f of 0.5 0.5. Okay, that means the gradient of a constant will be 0. So you will get 0 0. Right. So that means we cannot optimize the problem further. Why? Because the we cannot, we are not getting the direction in which the objective function is increasing. So we don't get the that direction. That direction is 0 0. So there is no point in searching for the optimal solution, because the mathematics is telling to us that you stop here. Why? Because it is the gradient is 0, so there is no such direction that the objective function is increasing. So that is why, if the gradient of a function is 0, then you stop there, we cannot optimize further. Okay, so that is the solution. Now now we will, yes, we will have another example problem. Actually, you should write this in your paper as assignment question number 2. Okay, assignment question number 2 is like this. The question is like this: minimize f of x1 x2 equal to x1 minus x2 plus 2x1 square x1 square plus x1 x2 plus x2 square. Starting from the point x1 equal to 0 0 0 0 vector 0 0. Okay, you proceed like what we have done in the previous problem. Okay, and submit your assignment when I have asked you to submit.